Hello everyone. In this video, we are going to talk about two different notions that sound quite a bit similar, but they are not exactly the same thing. And in some cases, they could be actually quite a bit different. One of them is called quasi-harmonic motion. The other one is called quasi-periodic motion. So what are these? Let's go through their definition and see in what kind of system these two are happening. And then we are going to show you also MATLAB examples, okay? So a quasi-harmonic motion is similar to a simple harmonic motion. So first of all, what is simple harmonic motion? We all know it, but that is basically a motion of this type, any signal that can be defined by a single amplitude, constant amplitude, a constant frequency, and a constant phase. Maybe even you can add a constant bias, but that's all it is. Frequency, phase, and amplitude, they are constant numbers. That is called a simple harmonic motion. And that's, for instance, what you can see in a mass spring system or in any system with a second order linear ODE that does not have the first derivative term and is homogeneous like that. Okay? Now, a quasi-harmonic is where the solution to the governing equation looks very similar to the simple harmonic, but your amplitude, your frequency, your phase, or any combination of them is not necessarily exactly constant. And it does change versus time, or it does depend on something else. For instance, omega could be depending on A, okay, or phi could be depending on omega or something like that. So when these guys are not perfectly constant, they depend on each other or they are changing versus time, although the form of the signal is similar, that is what we call a quasi-harmonic motion. Now, it happens in different scenarios, okay? And we are going to talk about them. But in terms of the governing equation, remember this simple ODE was the governing equation for a simple harmonic motion. But for quasi-harmonic, you're going to have an extra term here typically. And that term could be nonlinear. And it could be a function of, like for instance, position, velocity, time, and multiplied by some constant, where typically that constant is a small term. In other words, the nonlinear terms are typically smaller than the linear terms. So most of the time, it is coming from some nonlinearities in the system. Now, some linear systems, like the systems that are lightly damped, are also considered quasi-harmonic, and we're going to talk about them, but many times it is coming from a nonlinearity. So we can say that again, the solution resembles a simple harmonic motion, but with a small perturbation or changes to the amplitude, frequency, or phase. So let's look at the scenarios. The first scenario that you all know from damped systems in vibrations is if there is a damping in the system, but the damping is very small number like this. So this is the governing equation, and this C or zeta, the damping factor, which depends on C, is a small number. In that case, your solution is a harmonic function, okay, where this frequency is fixed, the phase is fixed, but your magnitude has a change versus time. It has an exponential decay. So when you have a damped response like this, you cannot call it a simple harmonic motion because your response amplitude does change versus time. So here you have that case of A of t. So this response is clearly what we call a quasi-harmonic motion as opposed to a simple harmonic motion. So this can happen in linear systems, of course. And this is why C should be small, because as I said, your response is very similar to the simple harmonic system, except for small changes. So if C is very big, then your response goes something like this, very fast, right? So, and in that case, it is not going to be anything similar to a harmonic. But here, when C is small, this drop that you see, this exponential function, this envelope, is going to be very gently, and you can even make C so small. In this case, I'll show you. The C that I picked is very small number. I can even make it smaller, so you can barely see these amplitudes are dropping unless you observe it for a good amount of time. Okay, so if you watch this, for instance, for 10 seconds, you would not see a significant drop in the amplitude. But yeah, of course, if you watch it for a longer time, you see that ultimately the amplitude is dropping. So it's very close to a simple harmonic, but with small changes. Now, this is first scenario. What else do you have? The second scenario is in a nonlinear system that has a harmonic response, but not perfectly simple harmonic. One case is the nonlinear pendulum. The other case is a weakly nonlinear oscillator called the Duffing oscillator. So this is a Duffing oscillator, okay? And if you want, on my channel, if you go and look at, search for the Duffing oscillator, you should be able to find the Duffing oscillator, right? So I talked about it. Let me show you. So this is my channel, and here we go. This is the Duffing equation and the Duffing oscillator. So you can see that basically, and I explained that if you want to know more about the Duffing oscillator. And here I even added a function on the right hand side. You can set it to 0. And the other thing I talked about, the period of nonlinear basically nonlinear oscillator. And this is here, and I'm gonna talk about it. So these parts that I'm about to talk about, they are referring to these two videos. One of them is period of nonlinear pendulum oscillation, and the other one is the Duffing equation. Okay, so if you want to know more explanations, refer to those videos. But if you look at a Duffing oscillator, the solution of that is approximated by a constant magnitude times a cosine function with a constant phase. The only difference is the frequency of this response has a term in it that does depend on the amplitude. So if you start the oscillator with a different amplitude, different initial condition, you are going to get different frequencies. So your frequency does depend on the amplitude in this case. Okay, so you can say omega is a function of A. It doesn't need to be always a function of time. It could be a function of something else. Okay, and that happens because of this nonlinear spring in the system. Okay, this nonlinearity and that alpha. And of course, the bigger the alpha is, the bigger the nonlinear, the bigger this dependence on frequency on the amplitude. Okay, but that is something you can see here in this the bottom left graph. As you can see here, these are the responses, numerical solutions to the Duffing oscillator. One with a large amplitude, one with a small amplitude, and if you can see, although they started from the same basically phase and initial condition, okay, except for of course magnitude, but the same phase, the same x dot of 0, you see that if it was a linear oscillator, if that alpha x cubed term was not there, their frequency would be the same. Their frequency both will be omega naught. But because of that cubic term, now you can see that the frequency of the blue curve and the red curve are different. Right? So if I zoom in, you can clearly see that over time. For instance, let me show you. This is like 2 period of that oscillation here, right? Like right there. And this is for the red one. Look. Or if you go like, for instance, 1, 2, 3, 4, 5 cycle, right? And then you can see it is basically here. So you see that the small amplitude and the large amplitude, they are getting different periods or different frequencies although they started from similar condition, except for the case of amplitude. And of course, the amplitude has effects on the frequency or the period in this case. The same thing happens for a nonlinear pendulum. For a nonlinear pendulum, as you know, if the pendulum is linear, the natural frequency is square root g over L, okay? But if this theta becomes sine of theta and it becomes nonlinear pendulum, then in a nonlinear pendulum, if you release the pendulum from initial angle theta naught with zero velocity, the period of the oscillation is not going to be constant. It is going to depend on the initial condition or the amplitude. And in here, you see this square root L over G is there, but you have this complete elliptic integral of first kind. And so, this function, there is no analytic solution for it, closed form with limited number of terms, but you can always numerically calculate this. And in that video, I showed you that formula. I provided another formula for it, but they're both the same. I mean, it is basically this guy expanded, okay, written as an infinite series. And clearly you see that the period, or you can say the frequency, does depend on the amplitude. And again, you can see that here. So here is the nonlinear pendulum released from two different angles. First one released from 10 degrees, second one released from 90 degrees. And you can absolutely see that again. Look here, this is like two full oscillations of 90 degrees. This is like two full oscillations of 10 degrees, or if you want to go a few more, for instance, right? So here I go two extra ones. This is after 6 full oscillations, and this one is after 6 full oscillations. So you clearly see that the period of the one with 90 degrees is longer than the period with the 10 degrees. Okay, so the period is an increasing function of the amplitude. And for that reason, although the motion is clearly similar to a simple sine wave, but it's not exactly a sine wave. And actually, that the solution to the nonlinear pendulum does not exist in terms of the elementary functions that we know in mathematics, okay? The solution of that is what we call a Jacobi sine function, okay? And that one is just a function that only exists numerically. You cannot analytically solve this. Okay, so that is a second scenario for a quasi-harmonic motion. So these are the cases for quasi-harmonic. Now, what is quasi-periodic? Quasi-periodic means the motion is not even periodic. It just looks like it is repeating, but it doesn't. The motion never exactly repeats, although it looks like it is, but it never does. And typically it is a system that has two or more frequencies in it that are incommensurate. Means the ratio of those frequencies is not a rational number, like any system like this. It has A1 cosine omega 1t and A2 cosine omega 2t, where the ratio of omega 1 over omega 2 cannot be expressed by the ratio of two integer numbers like m over n. You can never find any two integer numbers. If you divide them, that is going to be the ratio of omega 1 over omega 2, okay? If you have those two kind of incommensurate frequencies in your system, then the response will never exactly repeat, and this is called quasi-periodic. Okay, a quasi-harmonic motion is definitely periodic. It does repeat. The motion of a nonlinear pendulum repeats. The Duffing oscillator repeats. Okay, but the case, for instance, that you have a weak forcing in the system, that does not repeat. So if you have a mass spring damper system with an external force where the exciting frequency is not equal to natural frequency, but it is very close to it. Okay, so omega is close to omega naught, so it's kind of close to a resonance, but not exactly. And the magnitude of this exciting force is a small magnitude. Okay, so it's a close resonance excitation with small amplitude. And if you watched my videos under playlist vibration, one example that I provided was called the beat phenomena. Okay, so that is exactly this one here. So if you watch that video called the beat phenomena, you can see that in the system there are two frequencies in the response of the system. One of them is called omega average, which is like omega 1 plus omega 2 over 2. And the other one is called omega of the beat, which is basically 1/2 of omega 1 minus omega 2. And that omega of the beat is the frequency of the envelopes of this response. So if you draw envelopes of this response, you see that when the amplitude of this response gets modulated and changes, the envelope shows like a harmonic wave, and that has this frequency. And then the signal itself has basically a faster frequency, and that is omega average. So if you look at this response, it looks like it is repeating, but the matter of fact, if you zoom into it, it is never exactly repeating. Why? Because the two frequencies that I have in my response, omega 1 and omega 2, the ratios are not really a commensurate thing, a rational response. In this system, the way I simulated it, my omega naught was equal to pi. My capital omega excitation frequency was 1.1 times that, and the amplitude was just 0.1, and this is the response. And again, this response is not exactly periodic. It never repeats. You might say, well, look, it does. No. I mean, if you look at these two curves, at least look at this parts, right? Look here. Let me show you. So look at this portion and look at this portion. You might say they are exactly the same, but if you look at the difference in these heights, you see that that is not exactly the same. Here you have a little bit bigger peak compared to this one. So it gets very close to repeating itself, but it never does. This kind of motion is called quasi-periodic motion, and you see it in beat and in system with weak forcing. Okay, and again, if you want to know that, all you need is to go to my channel under playlist vibration and search for the beat phenomena, and there we go. Okay, and I explained this beat phenomena again in more details. So as I said, any system like that, and you can also see it in double pendulum as well, when it's not showing chaotic response, because it also has two frequencies in it, and those frequencies are not commensurate. Again, you are going to see this kind of response. So if I want to finalize this and summarize the difference between these different kind of motions or responses that you have seen, which one of these systems showing quasi-harmonic, which one is showing quasi-periodic, I can tell you that in nonlinear pendulum with no torque, in Duffing oscillator, and in linear systems with the small damping, you can say all of the systems, their motion is exactly periodic. It does repeat, but it's not a simple harmonic motion, because either the amplitude is changing versus time, or the amplitude affects the frequency or something. So yes, all of them are quasi-harmonic, but they are not quasi-periodic. On the other hand, a system that shows beating because of weak forcing excitation and close to resonance excitation, there will be two incommensurate frequency. That system will never repeat itself, so it's absolutely not harmonic. It is just similar to a periodic motion, which we call quasi-periodic. Okay, it's never actually periodic in the first place. So hopefully now you have a better understanding of the difference between these two important notions. And finally, here is my MATLAB code. So I simulated each and every one of these four systems, and all you need to do is to simply run it. So this is your quasi-periodic motion, the beat. Okay, and then this is your nonlinear pendulum for two different initial conditions or two different amplitudes. Feel free to change those. This is the Duffing oscillator, again for a smaller and bigger amplitude, and you see the frequency shift in them. And then here is the lightly system with small damping. And again, if you want to change that, you can make it even smaller. Okay, you can make it something like this, and then go here and change that. Now, even in 50 seconds, it is not easy to see that, right? So look here. You see, it is very small, even with 50 seconds, the amplitude. And if you plot it over 10 seconds, then absolutely you are not going to see much of a change, right? So all you need is to go, hey, I want to go from 1 to, let's say, round of length of t, and then over 5, right? Something like this. And then you should be able to get it to plot it only for like 10 seconds or so. Here we go. So here I'm just plotting it for 10 seconds, right? So I just limit t and response to 1/5 of the time instead of 50 seconds, to 10 seconds. And you see now your amplitude is slowly, very slowly is changing. And I brought c down to a very, very small number. So hopefully this video was useful to you. I'll see you in the next lecture. Thank you.